AP Chemistry, this is the answers video to the day 55-56 assignment. It's on rice tables, and it's important to become really familiar with rice tables. We're going to use them extensively in the acid-base unit coming up after Thanksgiving. What they simply are, they're used with equilibrium reactions. That is where you're going to have, at the end of the reaction, you're going to still have some reactants left and some products, and you need to figure out the concentrations of each at equilibrium. Equilibrium is dependent on certain things, such as the concentrations and the temperature or pressure, and it's so these are used for that. And all they simply do is they take the reaction, and then they take what the beginning concentrations are, or pressures. Then they set up an algebraic equation of the change in concentrations or pressures to come up with an algebraic expression for the equilibrium. And then knowing the equilibrium constant, you can figure out what those concentrations are. There's other problems, such as this one, where you'll be given the concentrations, or you'll be able to figure out all of the concentrations of the reactants and products, and then figure out what the equilibrium constant is at certain conditions, temperatures, pressure, so forth. Okay, so here we go. So the initial concentration of SO2 and O2 are 0.1 molar, and the equilibrium concentration of O2 is 0.75 molar. What is the value of Kc? So in this type of problem, what would be happening in the real world is chemists are trying to figure out what the equilibrium constant is at a certain temperature. Normally you would have the temperature given just to say that, okay, this is at a particular temperature, but I didn't do it in this problem. So you're going to be given, you're going to need to know all of the equilibrium concentrations, and with that you can put them into the law of mass action to come up with the equilibrium constant. So they would have had to go in and through an analytical chemistry in the lab, find out what the final concentration of O2 was in order to do this. So let's go ahead and plug in our values. So initial concentration SO2 and O2 are 0.1. I'm going to omit the trailing zeros here. First, we want to write the reaction. So we're going to do that. You write it exactly as you see it up above. And I like to draw the arrow here to remind me which side is reactants and which side is products. Otherwise, you might forget. You won't see that in books doing that, but I like to do it that way. Okay, so there we go. That's the reaction. Now the initial is 0.1, 0.1. And then the equilibrium concentration for O2 is 0.075. Okay, so it's almost like a little puzzle figuring out what the various, what goes in each of the boxes. Well, the first thing we see is if the initial is 0.1 and the final is 0.075, then the change is going to be the difference between those two. So we'll do that. So for O2, so it's going to be 0.025. It starts here, it ends here. That means you had to have subtracted 0.025 of the concentration. By the way, I like to write the coefficients of 1, even though it's not normally done. I like to do it. And here's why. Because if now we just look for relationships. If there's 2 moles of this, or 2 molar of this, and we just assume we're doing it in a 1 liter container, so moles and molar would be the same thing. And there's 1 molar of this and 2 molars of this, then if we know what this is here, it represents 1x. We can put that right here. So this over here is going to represent 2x. Well, we already know what x is here. You didn't really have to write these two things. We already know what x is, so this has got to be twice as much. So this is going to be 2 times 0.025, and it is decreasing. The reason for the negative sign is it's a reactant. It's decreasing in value. So this is 0.05, so that number is twice that number right there. And this number over here for change is going to be twice this number. And it's going to represent 2x as well. This should be a negative 2x and a negative 1x right there. This is going to be positive 2x because it's a product. It's increasing in value. They didn't give you any initial value for the SO3, so you assume it's 0, so we could have written that right away. Okay, and we have 2 times this number, and it's positive. So that's going to be 0.05, and that's a positive. You can write the positive sign if you want. Okay, so now we can figure out all of these right here. This equilibrium is going to be 0.05. If you take 0.1 minus 0.05, it gives you 0.05. And over here, if you take 0 and add 0.05, it's going to be 0.05. Okay, so now we can take these 3 equilibrium values. The law of mass action for this reaction is going to be the following. I like to write the general formulas always to help reinforce the concepts here. So it's going to be SO2, or SO3 rather. You don't write the coefficient in the laws of mass action, but they'll come later on here in a sec. Okay, so SO3, and since it's got a coefficient of 2, it's going to be squared. And that's going to be over SO2. Coefficient of 2, that means that's going to be squared. And O2, that has a coefficient of 1, so it's just to the first power. Okay, so that's what you have for that. So now what we're going to do is we're going to substitute in these values that we know here. So this one is 0.05. And since I'm doing math now, I'll use parentheses. It doesn't matter. You can continue with square brackets. And you're going to square that. Okay, you're just going to put the 0.05 in for this, and you get that. Then for SO2, and then for O2. I would recommend you to do this one step at a time. Don't try to do too much on the calculator all at one time. So here we go. So I'm going to do 0.05 x squared right there, x squared, and I'm going to hit equal. And I'm going to go ahead and write down that value. Again, I'm not going to try to punch too many steps into the calculator at one time. You want to have a paper trail when you're on a test, because you don't have a lot of time to check your work. You want to be sure you can see quickly, how did I get that number? You could go back when you're checking your work and do this again, be sure that is what you got. Whereas if you do everything in one step on the calculator, you've lost, you don't have any record of what you did. Okay, so down on the bottom, we have the same thing down here. You can see 0.05 squared. And then down here, it's 0.075 to the first power. Okay, well, these two are going to cancel out. You have that in the denominator. In other words, it's effectively 1 over that, which means you flip it. You take the reciprocal. So we're going to do 0.075. And reciprocal can be done one of 2 ways. I'll show you both. You can say 1 divided by, it's a little bit of glare on my calculator, 0.075 equals 13.3. Or you can say 0.075 x to the minus 1. That's the reciprocal as well. Same thing. And then so it's 0.75 to the negative 1. You hit equal, it's 13.3. So that's your value of Kc. There's no units of measure for an equilibrium constant. So that's your final answer. Okay. So RICE tables are just used to set up algebraic equations that you use to plug into the law of mass action, the equilibrium equation, to solve it. Okay, so here we go. What we're given an initial concentration of NH3, and according to the equation right there, it's a balanced equation. Just verify that it is balanced though. before you move on. Okay, it says at equilibrium pressure of NH3 is 0.8 atmospheres. What is the KP? So you do pressure problems exactly the same as concentration problems, all right? And so let's go ahead and fill this out. First of all, let's write the reaction. You want to write the plus sign there, you can. I don't. I do write the arrow to be sure I don't get confused which side is products and which side is reactants, okay? Because one side's going to be decreasing, the other side's going to be increasing. All right, so what do we have? Initial concentration of NH3 of 1. Again, just to keep it simple, I'm going to omit the trailing zeros. Okay? And that means since they don't give us initial concentrations for N2 or H2, we're going to assume that they're 0. We keep going. It says at equilibrium, the pressure of NH3 is 0.08. Okay. And then what else do they tell us? So what is the KP? So again, it's like a little puzzle. You have to fill in the rest of the boxes. So that since this side, the reactant side with the NH3 is the only side that has any initial concentration, that has to be going down, and these two have to be going up. Okay, just simple logic. Okay, so how do we get this number? It's going to be 1 minus 0.8 equals 0.2. Okay, so that means that this is going to be 0.2. 1 minus that gives you that. Okay, so this is the number we're really interested in, this. Okay, now, what does that represent if we were to write it as an algebraic equation? It would represent minus 2x. Very simply, the x represents unknown, although it is known. This is the way we would write it algebraically. It's a 2 because there's a 2 there. Whatever the coefficient there is a coefficient in front of your change variable. And since this is decreasing, it's a minus 2x. When we look over here, we see that this is a 1. And we know it's increasing because it started off at 0. So over here is positive 1x. So if this is 2x, then this is half. This is going to be half of that. This is 2x, this is 1x. Then this number is going to be half of this, okay? So I'm going to just write 0.2 divided by 2 equals 0.1. That represents 1x here, okay? All right? So 0.1, and it's positive because it's increasing since it's on the product side. Now, if this 0.1 represents 1x, this over here is 3x. And it's also increasing. So that means this number is going to be 3 times this number. This is 1x, then 3x is going to be 3 times that, so it's 0. Let me write that so you see it. So it's 0.1 times 3, because of the 3 there, equals 0.3. So this is the number we're interested in here, this one here. And now all we have to do is add. 0 plus 0.1 is 0.1. And 0 plus 0.3 is 0.3. So now that we have all 3 of our equilibrium values and actual numbers, not even algebraic expressions, we can now write the law of mass action and figure out what Kp is. So again, write it in general form. And actually, since it's pressure, you don't use the square brackets. You use parentheses. And the way you write it, the way you're supposed to write it is pressure of N2, so you subscript the N2. Okay, and that's to the first power, so we don't have to I'll put the exponent just for the heck of it. Okay, and then pressure of H2. And that's going to be raised to the third power because that's the coefficient. So products on the top, then reactants on the bottom. Okay, and that's raised to the second because that's the coefficient in front of that. Now we can plug in the numbers. Okay, so the way I would do this is I'm going to take 0.3 to the third power, come up with an answer, multiply that by 0.1, because 0.1 to the first is just 0.1, and come up with my numerator number. Again, I don't want to do too many steps on the calculator at one time. It makes me nervous on a test to do that. Okay, so 0.3. Get it so you can see the calculator. Hold it up a little closer. 0.3 times, whoops, I blew it. 0.3, and then caret. You can see that to the third power, and that gives us 0.027. There you can see that a little better. And then we're going to simply take that, just leave it on the screen. You don't have to clear it or rewrite it. Then times 0.1. That's to the first power, so it's just 0.1. 0.0027. So the numerator here is 0.0027. 0.0027. Down on the bottom it's 0.8 squared. So we're going to do 0.8. And then we're going to hit the x squared button right here, x squared. And there you can see it's got a, if you can see it, it's got a 2. 0.8 squared, and you hit enters, and it's 0.064. Oops, it's 0.64, no 0 there. Okay. Now we simply do this divided by this. Okay, and when we divide 0.0027 by 0.64, we get our equilibrium constant for pressure for 0.0042. No units of measure. So that takes care of that problem. Okay, here we go on to problem 3. So find Kc. Again, we're finding an equilibrium constant. We're given initial concentration, 0.1 molar of H2 and I2 are present initially, and 0.134 molar of HI is present at equilibrium. So again, fill in the appropriate spots. First of all, write your reaction. All right. So we have 0.1 here, an equilibrium value. So it goes on the bottom line. All right. So we start off with no concentration of HI. Again, when it's not stated, you assume that. You can't do the problem if you don't assume that. So there it is. And we know that the HI is going to be increasing because it has no beginning concentration. So that has to be going up. So it's going to be plus, you just go ahead and fill in this box. 0 plus what number gives you 0.134? It's 0.134. And that represents positive 2x. The 2 because that's the coefficient, and it's positive because it's increasing. So over here we have coefficients of 1. And they're going to be decreasing because you started off with something and they're going to go down. All right, so if this is 2x, then this is going to be 1x, and it's going to be negative 1x. And so is this one over here. Okay? In other words, this number is going to be half of this number. If this represents 2 times x, this over here represents 1 times x, so x is going to be, this number is going to be half of this number. Again, it's a 2-to-1 relationship. You have twice as much of this as you do of this. So whatever this number is going to be 1/2 of that. So we'll just divide 0.134 by 2. And that gives us 0.067. And it's negative because it's decreasing. Same thing over here. You have twice as much of this. There it is right there, that number, twice as much as you have of this. So that one has to be half of this as well. And these two are decreasing. 0.067. Gotta watch those zeros. I didn't write these down correctly. So that's 0.067. It's half of this value right here. Gives us 0.033. Then the same thing. Okay, so now we know the equilibrium concentrations of all three, both reactants and the product. So now we write the law of mass action. We're trying to find Kc. So come over here. Now we plug in the numbers. And of course, you can't use square brackets on in Excel or on a computer or in a calculator. You have to use parentheses here. Okay, and now we just go ahead and solve. So 0.134 squared. Hit x squared here. It equals. And now I divide by 0.33 two times. Divided by 0.033 rather. Equals. Divided by 0.033 equals. And we get 16.4 for our KC. 16.5 actually. Okay, and that's that. That takes care of that problem. I've left you a lot of space here because what I'd like you to try to do now is cover this up with a piece of paper and go down, leave this part uncovered, and go down and see if you can redo the problem, even redrawing the rice table again. See if you can do the problem on your own. That's when if you can do it a couple times like that, that's when you really know how to do it. If you know how to do this problem, you can do it in about 2 minutes. Okay, you'll get to where you start doing these rice tables in your head if you practice them enough. Okay, we know what that's going to be right away. You know what that is. If that's 0, you do that in your head. You realize the relation here is 2 to 1, 2 to 1. So these values are going to be half of this value, and so you start almost doing these things in your head. Okay, now we move on to problem 4. So if the equilibrium concentrations of N2 and H2 are 0.5 and 0.1 molar respectively, that word respectively means in the same order. So N2 corresponds with 0.5 and H2 corresponds with 0.1. So that's what the word respectively means. Now, this is key. These are equilibrium. You got to be sure whether they're equilibrium or initial concentrations. What is the equilibrium concentration of NH3? And they give you a K equilibrium. So we're going to go ahead and create a rice table. Gives you a chance. It says create a rice table, so we're going to do it. So a rice table has to have 4 rows. Here. And it has to have as many columns as reactants and products together, plus I add one for the words rice, that rice stands for. Okay, so let's go ahead and fill it in. So the equilibrium concentration, let's write our equation first. So it's 2NH3. Let's do that first. Again, I like to write the arrow to remind me which side is products and which is reactants. Okay, so initial equilibrium concentrations, N2 is 0.05. I'll omit the trailing zeros. And H2 is 0.1. Okay, and what it wants to know is what is the equilibrium concentration of NH3? That's what we're trying to find. And it gives us a K. Well, you have 3 out of the 4 things that go into the law of mass action. You have the equilibrium concentration of N2, of H2, and you have the K. And they want you to find the 4th, which is the NH3. So we really don't need to do anything with the rice table here. And if you had spotted that and you had some, when you get some experience with these problems, you would have realized that you didn't really have to write the rice table. So let's go ahead and write the law of mass action. These are gases. We could call it Kp, but it's just K equilibrium. They called it this time. Okay. Okay. So this is the one we're trying to find. So we can go ahead and plug in our numbers. K equilibrium is 3.81. Let me draw an arrow there. Okay, so NH3 is our unknown. Alright, hopefully the algebra on this isn't too tough. Both sides by this. This cancels out on the right. Divide both sides by this. This comes over here. So really that's the only 2 steps. So let me say that again. So the 0.5 and the 0.1 stay in the same place. Okay, so this came down here, divided both sides, and this came up here. You multiplied both sides, so that's what you have right now. And now you go ahead and solve it. 0.1 caret 3 equals, and that gives us some number, 0.001 times 0.5 equals 0.0005, and then you divide that by 3.81, and that gives us 0.00013. Okay, and that equals NH, the concentration of NH3 squared, but we want NH3. So we're going to come down here, and we're going to take the square root of both sides. So this simply becomes NH3, and this becomes 0.0114. And that's our final answer for the concentration of NH3. Okay, so here we have a chemical reaction, synthesis reaction for nitric oxide, and it says 0.5 mole N2 gas is mixed with 0.86 moles O2 gas in a 2-liter tank at 2000 degrees Kelvin. Again, the only reason for giving you a temperature in these problems as well as kinetics problems is just to say that, hey, the temperature that what you're finding is concentrations at a specific temperature, and that temperature isn't going to change. You don't need to plug that number in anywhere. Okay, so what are the equilibrium concentrations of each substance? And we'll go ahead and figure out the equilibrium concentration of NO2 as well. Okay, so the trick to this problem is to realize that equilibrium problems, the law of mass action, let's write that first just to emphasize this point. So we're looking for, we have a K equilibrium, which is really, again, these are gases, so it's really a KP, but we can just call it K equilibrium. So what's this going to be? It's going to be on the top because it's a product. And the coefficient makes it a square. Okay, so that's the law of mass action for this equation. Now the key to this problem is to understand the point that the law of mass action and equilibrium problems must be done in terms of molarity, moles per liter, not just moles. If you just plug in moles, you're going to get a wrong answer. So we need to compute this, we need to convert these moles into molarity. How do we do that? Well, moles per liter. We have the moles, and now over here we have the liters. Okay, so what you have to do is come up here. We'll do this calculation up here. That molarity for the N2 equals, again, I'm going to omit trailing zeros, and it's 2 liters. So that's the molarity of the N2. We do the same thing for O2. So there's our two reactants in terms of molarity. Now we can plug them in to the law of mass action, use them to compute compute the variables here. Okay, so let's write down the reaction. Okay, so these are initial values here that we just computed for molarity. Okay, and then we assume, since they don't give us any initial value for the product NO, we just assume it's 0. Okay, so now we're going to set up our change line, and it's simply going to be on the reactant side, it's going to be reduced. So it's minus, and it's 1 molar there, so we put a 1 in front of the change variable x. Again, we don't know what x is yet, so that's why we use it. It's algebra. Okay, and then here, same thing. It's minus 1x. And over on the product side, we start with 0, so we can only go up. So it's going to be plus 2x. Okay, hopefully that's starting to kind of make sense. How you do that. So now down here we simply write this. It's simply 0.25 minus 1x and 0 plus 2x there. So now we have our algebraic expressions that we can now plug in to the law of mass action. Just leave the 1 off now. It's just minus x. Okay. And that's going to equal our K value, which is 4.1 times 10 to the negative 4th. right there. Okay? Okay, now if you do the algebra on all of this, it's going to be a big, ugly quadratic equation. And it's going to be messy to solve. You have to use the quadratic equation to do it. And the quadratic formula. And I told you would never have to use this because we can use the simplifying assumption. It says you may use the simplifying assumption. So down here we have 0.025 minus x. If we assume that x is much, much, much smaller than 0.025, we can simply eliminate it because 0.025 minus some really, really tiny number is going to basically just be 0.025. Same over here for the 0.43. And I don't know how I got a 0.25 in there. That should be 0.25. Let me correct that. Same thing for the 0.43. If we assume that x is much, much, much smaller than 0.43, then 0.43 minus a really, really, really tiny number is just going to basically be 0.43. So we can just x those out. Now remember what we said also in the lecture video, you can't x out, get rid of an x that's being multiplied. Okay, you can only do it if it's added or subtracted. In this case of these problems, it's generally being subtracted, but sometimes not. So we can rewrite this equation down below as follows. Now what I'm going to do is expand 2x squared. So 2 squared is 4. So I'm going to go ahead and just do that right now. And then x squared is x squared. So this is equal to 4x squared. Be sure you understand that. And then down at the bottom we simply have this. Okay, so now what we're going to do is multiply the top of both sides by 0.25 times 0.43 and divide by 4. We're trying to get x by itself. We're solving for x. So over here I'm going to do the same thing. Okay, so over here, cancel, 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 cancel. So all you have left is x squared. That's what you want. Over here you multiply 0.25 times 0.43 times 4.1 and then divide by 4. So I'm going to come down here. I'll put the x squared over on the left side of the equal sign. And we'll go ahead and do 0.25 times 0.43 times 4.1 divided by 4. And that gives us this. Okay, and I'm rounding it to 2 digits. And then don't forget this, to put this back on here. Okay. All right, now we're going to take the square root of both sides. And what we get is x equals 0.0033. Okay, so we have used the simplifying assumption to get to this. Now we need to see if it's valid to use the simplifying assumption. And that is that the value of x, which is 0.0033, is much less than the initial concentrations, and that would be 0.25 or 0.43, then it's valid to use the simplifying assumption. In other words, just ignoring x was okay to do. Now, the one we need to test against is this one. It's the smaller concentration of the two. So if x is less than the smaller concentration, if it's less than 5% of the smaller concentration, then of course it's going to be much less than 5% of the larger concentration. So we only need to test it against this. So what we are going to do then is say, and now we just run that calculation to see if it comes out to less than 5%. And it comes out to be 1.3%. So we're okay. Now we still haven't answered the question. What we figured out is the value of x. What we need to do is come back to our equilibrium algebraic expressions and plug x in for these. It was asking us for the concentration of N2 and O2 and of each substance. So all three of them. Okay, so we just go down below and do that. So the first one is for N2 is 0.25 minus x. So we'll come down here it gives us this. It's pretty much 0.25, all right? If you round this up, you go to just two significant figures, it would be 0.25, but I'm going to go ahead and write it out to 4 digits so you see it is a little bit less than that. That's what it's saying. For O2, it's 0.43 minus X. Again, go back to the equilibrium line of the rice table. That's where you get this equation from. Okay, and then for the product side, compound, NO, it's 2 times X, again from the equilibrium line of the rice table, so it's 2 times, and that's 0.0066. And these are all molar, so we should put an M. They're concentrations, and that's what the question was asking for. What are the final equilibrium concentrations? There they are. That's your final answer for that. Okay, and now we're on to our final problem. Number 6, the equilibrium constant for this reaction is 60.2 at 250 K. If the initial concentrations of hydrogen and iodine are both 0.25 molar, what is the equilibrium concentration of HI? Alright, so I give you the answers there, but let's go ahead and work through this together. There's a little bit of a twist to this problem. So I'm trying to give you problems on this in this assignment that are a little bit different in some way, because you're going to be doing a lot of these rice tables in the next few weeks. So I want to give you kind of a variety. We're doing all of them together, and I want to give you a variety of situations here. Okay, so we're going to go ahead and this. Okay, so initial concentrations. And nothing stated for HI, so we put it as 0. Coefficients in front of H2 and I2 are 1. Our change variables will be product, so it's positive over here. Okay, I'll take the 1 off at this point. Okay, the law of mass action. It's a gas reaction, so we can still call it concentration. Even if it's gases, it can still be a concentration. We can plug in our algebraic expressions. Okay, so now we're going to go ahead and use a simplifying assumption, which means we can get rid of that x and that x, not that one. So what that's going to give us over here is this. I'm going to go ahead also and simplify 2 squared is 4 and x squared is x squared. So it's 4x squared over 0.25 squared. So let me come down and plug in the value of Kc. Go ahead and continue over here. So I'm going to solve for x squared. I'm going to multiply. Let me go ahead and do it right here. Multiply the top of this side by 0.25 squared, and divide the bottom by 4. So all of this is going to cancel out. You just give us x squared. It means we have to do the same to the other side. I'm going to move the x squared over to the left side here. So what we have then is so 60.2 times 0.25 times 0.25 again. That's the 0.25 squared divided by 4. And that gives us this. For x. Okay, so what we're going to have to do, we can't use the simplifying assumption because that x is bigger than it's even bigger than the initial concentration. So what do we have to do? We're going to have to use our original equation without canceling out the x's, which normally means the quadratic formula, but fortunately this problem left us an alternative that's easier. The fact that these two concentrations are the same and that these two values are the same presents us with a 0.25 minus x times 0.25 minus x, which is 0.25 minus x squared. So what I'm going to do is come down here and rewrite this equation down here. Okay, so we have Kc, which is 60.2. We have the 2x squared up on the top. And 0.25 minus x, 0.25 minus x. So we're going to call that 0.25 minus x squared. Now normally this would lead to a quadratic formula type of problem, but the good news is since we have square on top, square on bottom, we can simplify it to this. Take the square root of both sides. And again, I'm going to simplify this immediately to 4x squared. Or I didn't really need to do that actually, but I did it. So okay, so that's going to equal, I really could have just taken off the square now and made it 2x, or take the square root of 4 is 2, and the square root of x squared is x. So you have 2x on the top, and now down here you just have 0.25 minus x. There's no longer the square there. The square went away. Okay, and then the square root of 60 is 7.76, so I'm going to come down here and write that. I'm going to multiply both sides top and bottom. Do that first. Multiply both sides top and bottom by this. It's still a little bit of messy algebra, but you're not dealing with a quadratic. And the same thing over on this side. Cancel, cancel. And so we multiply this through, and we get 7.76 times 0.25. And that gives us 1.94 minus 7.76 times x is 7.76. X equals 2x. We're going to add 7.76x to both sides. Disappears on that side. So you have 1.94 equals 2 plus 7.76 equals 9.76x. Okay. We're going to divide both sides by 9.76. This is all algebra, no chemistry here. It's all integrated math 1 and 2. I'm going to bring that over here. I'm going to draw a little line here. And that's going to give us, that cancels out, so x equals 0.19 to 3 digits, okay? So that's your value of x. Now, if you want to know the concentrations here, I'm going to go to a new piece of paper, clean piece of paper, because I'm at the bottom of this page. So that's our value of x, and up here are our values of H2, I2, and HI, so we just plug it in. Okay, so I'm going to come here, and for H2, it's going to be 0.25 minus this value of x we just came up with, 0.199. Okay, it's going to be the same for I2, and finally for HI. Okay, so we can see that our values of x are not very small compared to 0.25 and 0.199. Again, think of it like 19 compared to 25. 19 is not very small compared to 25. So anyway, this is a problem where fortunately we didn't have to use the quadratic formula, although normally you would, when you can't eliminate the x's as we tried to do here. So we tried to do it, we found that we couldn't, so we had to go back. But fortunately, because of the quirk that these two values here are the same, you could square them, and down here we were able to square them and then take the square root, and it simplified the problem. At least it seems like it simplified. But that's your final answer for this. Okay, so practice these. We did every single one together, but practice them because you need to be good at these for acid-base equilibria problems that will be coming up in the next 3 weeks. All right, we'll see you on the next lesson.